Hello, Rajita ma'am.
Yes, Sandeep.
Ma'am, actually, Zoom they have updated today.
Okay.
In fact, in before we didn't have this waiting room or anything. So for this room, there is one pass code. I will give it so that we can share it with the students. From next class, I think we will put pass code.
Okay.
Because till last week they didn't give this option. From this week, it is like this.
Okay, right.
So I am admitting already at present now the strength is 175.
Okay.
Students, they have to log in quickly, otherwise it will be difficult.
Okay.
That's
Let me give the information to them.
I'm already informed them.
Yeah. I saw that chat.
I think they can check in the chat box. I think once 200 it crosses, I think I'll give you the host permission.
Okay.
You need to give them admin access, otherwise they'll be in waiting room.
Okay. Will we wait for 5 minutes, Sandeep sir?
Yes, ma'am.
Now it is 200 members.
Yeah, 200 exact.
Exactly.
I will give you the host permission, ma'am.
Okay. I have to assign them as admin passwords they have to give.
They will, you just need to admit them, ma'am, into the room.
Okay. Then I have to click that. So I'll ask Prabha madam. Will you give the permission to Prabha madam?
Ma'am, only two people. One is me and one is you. That's it. There are only two hosts. We didn't take multiple hosts.
Okay then.
Yes. So you need to click on admit so that students get in.
Where we have that admit, we have 9 people are entered in waiting room. Okay.
Yeah, ma'am. Just click on admit all. All at once you can admit.
I'm not getting.
Not getting. 1 second, ma'am.
Yeah. I have. Admit. There is a blue color.
Yeah, blue color button is there, ma'am. On top you will get admit all.
Yes.
So if you click all.
Admit all. Okay. I just clicked it.
That's why I didn't give you the access actually.
Okay, okay. No problem.
I was giving on admitting all.
Yeah.
And you are
Uh,
able to see the recording option and everything, right?
yes, yes. Recording option
Yes.
in reaction.
And then there
Share
is
the
something
screen
on
chart,
the
participants
disable
security.
annotation, ma'am. That also you take care once.
Which one?
A disable annotation. In the screenshot I sent you, no? In that it
Uh,
is there.
okay,
Disable annotation that you need to take care once.
okay, okay. Okay, disable participant and annotation.
Annotation, yes, ma'am, right.
Uh,
Is checked
yeah,
or
yeah,
unchecked?
yeah, yeah. I'll check that. Now I'll check it. 1 second.
Check, then I think it will become enabled, ma'am. Disable is there, then okay, I think.
It is not showing any remote control more or some options. It is not showing. Can I have
It
to
is
move
not
to
showing.
security? I have to move to security option.
Security only, I think, on that option is. Yeah,
Security,
it's
allow
security only.
parties in security,
It is.
unmute themselves.
Security or more.
More is not there. Security is there because the options are
Okay, security.
visible,
In that,
which are visible to you that are not available for me.
mm,
In security, I have the options remove participants, unmute themselves, rename themselves, chat, share screen, allow
okay,
participants
then
to
in record, ma'am,
in record. Okay.
I think once
Record
you,
on only two options, record on this computer and record on the to the
I
cloud.
think once you start recording, I think you will get that option. Enable and
Okay.
disable annotation. Once you
Yes.
start recording, I think it will come.
Now I started recording,
Yes.
but I did not get any options like
Okay, ma'am,
annotation.
leave it. Leave it, ma'am.
Okay, right.
And carry on, ma'am, with the session. I
Yeah,
will
yeah, yeah,
leave.
definitely. So
Okay.
all 251 are there.
Yeah,
Okay.
ma'am. Just
I'll click again. I'll click admit all after
yes,
5 minutes. Okay.
after 5 minutes, and then till then you carry on.
Okay, right.
Okay. I will leave
That's
the
it.
meeting.
Yeah. Thank you. Good evening, students. In last session, we have discussed about the biasing topics, transistor biasing, what is the need of biasing, everything we have just cleared it, and how many types of biasing. So which one is suitable as an amplifier? So which could be preferable? So if I wanted to use your transistor as an amplifier, which biasing technique is suitable that we have covered in last class. So now we're going to deal with some of the similar topics about your biasing only. So in that biasing, we have some characteristics like stability. So if you have low stability, what will happen? So next, what is the need of stability? Next, what are the compensation techniques we have in biasing? So next, we have some definitions like thermal runaway. So those are all the things we're going to learn today. Okay, right. I'll admit all you. Only 14 members are there in the waiting room. So now, Now, today's session is stability. What is the definition of stability? So, why we need to stabilize our amplifier circuit. Next, what does mean by thermal runaway? And some of the techniques to bias in biasing techniques. We are how to compensate that biasing. So, and how to improve our stability. That all the things we are going to learn now. So now, before we are moving, just we'll take a review about your last session. Now, so what is the need of biasing? Biasing, what is biasing? Applying you some DC voltage, which helps the functioning of the amplifier circuit. So now that amount of applied voltage can maintain a constant voltage of output voltage and a constant current collector current. Thereafter, we are going to superimpose an AC signal on that DC values. So based on this DC signal amount of magnitudes of quiescent value, we'll call that as a operating point, operating voltages. Why we call that as a operating voltages are, so these are the voltages which are given at the input and output junctions to in order to make the transistor as an amplifier. So hence these are also called the quiescent values, or we can also call that as a operating voltages and currents. So now let me move to our session. So now we already discussed that if this is called as a DC load line. Why we call this as a DC load line? Because it is a line which can be drawn between the two nodes. One will be A and another one will be of B. So A B. So next, so the line which touches these output curves is the region of linear region, or we'll also call that as a active region active region. And the extreme end will be your saturation region, and the extreme low end will be the cutoff region where the collector current is zero. Now, why we have placed that operating point exactly on the center of the load line, DC load line, is in order to obtain the faithful amplification. 1 second, I wanted to check how many members are again in waiting room. So now I am going to stop this screen sharing. Now 22 members are waiting. So why today's strength is very less? Only 292 out of almost 500. Quickly log in Dana. Already you had your break 10 minutes. Again 10 minutes ago. You are taking a total 20 minutes of break time. Please change your names like in the format given, your section, your roll number, and only will give the attendance. Right. So what does mean by biasing? So applying your DC voltages. Next, the circuit which provides your Transistor biasing is called as a biasing circuit. Next, if a proper DC voltages can maintain a constant current and a constant output voltage. So thereafter, we are superimposing your AC signal for faithful amplification. We have to keep the operating point on the exactly on the center of the DC load line. So if it doesn't put your operating point on the DC, like exactly at the center of the DC load line, then so we have a distorted signal at the output. So in order to obtain the distortionless output, put your operating point exactly at the center. So if you are putting at the extreme end, so just look at over here. So now I'm applying an input of AC signal here, whereas here now, one part of the signal is fully transmitted, but the other part of the signal, because if I'm taking a CE amplifier, so CE amplifier will provide 180 degrees phase shift. So when it provides the 180 degrees phase shift for the positive cycle of input, we'll get a negative cycle, and for the negative cycle of input, we'll get a positive cycle of output voltage. So now this amount of voltages which are amplified, since our current is also amplified with a beta factor, so where the beta factor is in the range of 20 to 400 range. So now our voltage is also amplified. So if I'm giving a millivolt of signal as an input to the CE amplified stage, I'll get in terms of volts. So almost it is multiplied 200 times or 400 or 500 times. It depends on the current gain of the transistor which you used, whether it is a PNP transistor or NPN, or the silicon or germanium transistors. Now, okay, right? So now let I move. First, if I place the transistor, because my collector to emitter voltage, so I wanted to apply. I wanted to put my operating point at exactly at the saturation, because since that VCE, if it is less, I mean, more positive, then your output junction is reverse biased. Now, when VC is moving towards the negative, then our output junction become forward bias. Hence, due to that, amount of current flowing through IC is maximum. So when it is IC is maximum, but one part of the signal, so your positive signal is now at the output, it will be converted into negative 180 degrees phase shift due to 180 degrees phase shift. So half part of the signal is distorted, and only the negative half cycle is allowed, because the below operating the area below the operating point is your linear region, where it is an active region. So it allows your negative cycle. Hence, we got the positive half cycle at the output. Whereas for the positive cycle of input, it is exactly at the saturation. Since that, so our output is experiencing some amount of your distortion. Hence, the power loss will be very high in your, if we are placing your operating point exactly at the saturation. Next case, if I'm placing my operating point at the cutoff, so below your IC. So when IC is zero, IC is equal to zero. So then that region is known as your cutoff region. When it is at cutoff region, so now we have superimposed an AC signal on this applied DC. So through your DC voltages, you're making your base to emitter junction forward, and base to collector junction is reverse biased. So now with that values, now my operating voltage of VCEQ, or the quiescent values of VCEQ and ICQ. ICQ is almost it is zero. VCQ is maximum. When it is maximum and ICQ is zero, so only half of the part is transmitted fully with the amplification, but next half of the part, because now we transferred your input signal. Now we have 180 degrees phase shift. Now for the positive signal of input, because my operating point is just above the operating point, you have a linear region. Hence, so at the output of your circuit, so we have a total negative half cycle, whereas for the negative cycle of input, if I am applying here, now, so you are applying a negative voltage. So when I am applying a negative voltage, then some part of the output will be distorted. So since this, So your operating point must be exactly at the DC load line for faithful amplification. You need to, in order to retrieve back your signal as distorted less signal at the output, so we have to apply a proper biasing conditions on your transistor. So now, so these voltages and currents, output voltage or the quiescent values of output voltages and currents are maintained using the amount of magnitudes of your applied DC voltages on input as well as on the output. Now, right. Next, stabilization. So, what does mean by stabilization? So that we have to discuss now today's session. So, the process of making your operating point, which is independent of your temperature changes of variations in the transistor parameters. So now, if the room temperature increases, so your can silicon and germanium can withstand a temperature or within a temperature ranges of 225 degrees centigrade for your silicon. So it can withheld 125 degrees centigrade to 225 degrees centigrade, whereas germanium it can up to 60 degrees centigrade to 100 degrees centigrade. So if it is above the 100 degrees centigrades or 225 degrees centigrades, then so these temperature changes can disturb the quiescent points or on the DC load line. So the variation in the quiescent point, which can move that the operating point either off into the saturation or into the cutoff region. Hence that we have the distorted output and we have a more power loss. So in order to reduce that, so we require some stabilization techniques. So now, so here the collector current and your collector voltage must be independent of your temperature variation, so or your replacements of your transistor parameters. Now we require a good biasing cycles for stabilizing your operating point. Now need for your stabilization, so your temperature, so stabilization of your operating point has to be achieved due to the following reasons. So now temperature is dependent on IC as well as the individual variations. Next, thermal runability. So now, so we have to stabilize our amplifier due to these three reasons. So now temperature, first one is temperature is, so your IC is dependent on your temperature variation. Next one is your IC is also dependent on the individual variations. Is nothing but your, for example, if I change my transistor from silicon transistor to germanium transistor, or if I took here another transistor in our circuit, if I replace the transistor with the same type of the silicon transistor, another transistor if I use, so might they have the beta variation from no two components are having the same similar characteristics. Hence here, so due to those variations, so those parameter variations can change your characteristics of, or your changes here collector current. If the collector current changes, then the operating point also changes from the DC load. It will move away from the center, either into the saturation region or into the cutoff range. Due to that, we have here the distorted output at the amplifier. So in order to avoid that, we are going to do the biasing techniques. Next, temperature dependency of IC. How this collector current is dependent on temperature variation. As we know that, so in your common emitter configuration, the output collector current IC is equal to beta IB plus ICEO. What is ICEO is, so this is the reverse saturation current. Whenever this is, we are discussing about your common emitter configuration. Hence, whenever the base to emitter junction is open circuited, or your base terminal is, your input terminal is open circuited, some leakage current is transferring towards your output junction due to the applied reverse bias at the output junction of collector to base junction. So hence here that ICEO is the reverse saturated current or the leakage current due to the output junction is reverse bias. Now, so beta IB, beta is nothing but the your transfer factor or the current gain. So it is the ratio of your collector current to the, or your output current to the input current. In common emitter configuration, our output collector output current is collector current, and our input current is your base. So hence, so it is equal to sum of beta times of IB as well as the leakage current. Why we are mentioning this leakage current is whenever the base is open circuited or the input. So we are discussing about common emitter. In common emitter, base is the input terminal. When base is open circuited, so then a small amount of current will flow to the output junction. A very finite amount of current is flowing through the output junction due to the reverse biased junction, or reverse biased collector to base junction. Hence that is termed as a ICEO. So it can be equal to beta IB plus of beta plus 1 times of ICBO. So ICEO, we just have just modified that into beta plus 1 ICBO. ICBO is the leakage current in your common base configuration, in common base configuration, right? So now operating points need to be stabilized. So now it is necessary to keep your collector current constant. Now, so already we discussed about what are mean by the individual variation. As the value of your current gain and the base to emitter junction voltage, input junction voltages are not same for every transistor. So whenever we replaced a transistor in the amplifier circuit, the operating point tends to change. So hence, it is necessary to stabilize your operating point. Next, next, next point is how this collector current is changing due to the thermal runaway. So now, if the temperature increases, so we already discussed that. So your silicon, it can held up to so 125 to 225 degrees centigrade. But germanium can withstand the maximum temperature range up to 60 degrees centigrade to 100 degrees centigrade. If temperature increases beyond these ranges, then the transistor burns out. So the increase in junction temperature is due to the thermal runaway. So now what does mean by a thermal runaway? The self-destruction of an unstabilized. So we are not biasing properly. If we are not biasing properly, If your transistor is an unstabilized transistor, then the self-destruction due to your temperature increase. So at the junction, due to the temperature increase at the junction can cause the thermal runaway. So now, due to this temperature, the cumulative action of your charge carriers accumulation takes place at the output junction. And next, that cumulative effect also yields to the temperature dissipation or the increase of heat dissipation. Hence, in order to avoid all these three parameters, which can cause the changes in the operating point movement from your center of the load line to the extreme ends of saturation or extreme low end of your cutoff region, we require the stabilization techniques, or you require the proper biasing circuitry. Now, so we have here a equation in your common emitter, sorry, common base configuration. So IC is equal to, like in the previous slide, we have discussed about common emitter configuration. Now, in common base configuration, the amount of output current is equal to alpha IE plus of ICBO, where alpha is the current gain of your common base configuration. So now, so so actually IC, if I neglect this leakage current ICBO, if I neglect this So, in common base configuration, our input current is emitter current and our output current is collector current. So now, so IC is output collector current is equal to alpha times of IE. If I neglect here the leakage current ICBO. Why we call this as ICBO is, here in common base we are just open circuiting your emitter. So when our emitter or input terminal is open circuited, some amount of leakage current is transferred through the output junction due to your applied reverse bias at the output junction of collector to base junction. So that is designated with ICBO. So reverse saturation current or your leakage current or open circuited emitter current. So ICBO is the open circuited emitter. If emitter is open circuited, then the amount of leakage current is designated with ICBO. Right now, I'm replacing IE. Generally in NPN or PNP transistor, it is equal to the summation of base current and the collector current. If I replace that with IB plus of IC, then IC is equal to alpha IB plus alpha IC plus ICBO. Now, so if I'm rewriting for this equation with IC equal to, we'll get as alpha divided by 1 minus alpha into of IB plus 1 by 1 minus alpha into of ICBO. As we already know that the relation between your current gain in your common emitter and common base, beta is always equal to alpha by 1 minus alpha, as well as beta plus 1 is equal to 1 by 1 minus alpha. And we replace alpha by 1 minus alpha with beta and 1 by 1 minus alpha with 1 plus beta into of ICBO. Whereas here 1 by 1 minus alpha into ICBO is equal to ICEO, where ICEO is a leakage current in common emitter configuration, whereas ICBO is the leakage current in your common base configuration. Whereas ICU, what is the relation between your ICU and ICVO is ICEO is equal to beta plus 1 times of ICBO. So where this ICEO is the leakage current in common emitter, where ICBO is the leakage current in common base configuration. So now, so here if I change, now just look it out here. Now this is your leakage current. Now this next beta. Now if I vary the beta, so if ICEO is in the range of nanoamps or in the range of microamps. So now, so next here, where here IB is in the range of microamp, beta, but beta is in the range of 200 to 500, 20 to 500. So now, so it must be multiplied with your IB current. So if I neglect ICU because it is very fine, very small amount of current, I can neglect the ICU. Whereas collector current is now depends on the beta factor. Now now if I wanted to explain you thermal runaway, so due to the junction temperature increase, the cumulative charge carriers uh, due to your increasing accumulated charge carriers. So accumulation of charge carriers, we have a high amount, a very high amount of collector current, and that high amount of collector current can raise the junction temperature. So this nature is again, so there is occurrence of your cumulative effect which increase your heat as well as the heat dissipation. So hence this heat will be totally dissipated into the collector region which is having the highest area in the out of the all the three regions. Now, so if that dissipation of heat energy is beyond the values of given, so then so the self-destruction of your transistor takes place. So now the self-destruction of your transistor is known as your thermal runaway. So now if I'm not stabilizing your transistor properly, then so your transistor will be damaged. So hence in order to avoid these three effects, we have to properly bias your circuit. Out of the biasing techniques, now we have your voltage divider biasing is the most popular one since that the stability is so it is very good in your voltage divider biasing circuit rather than your only four techniques whatever are the left four techniques collector to base bias fixed bias and emitter bias. So voltage divider biasing is the most popular and more stabilized biasing technique which can be we can obtain more stability and we can avoid this all the three parameter variation which can cause the IC change. Right. Next, I'll move to the next slide. Okay. Is it clear, everybody? Yes. Is it clear? Yes. Quickly check. Respond, Nana. Till this, is it okay? Right. Now, our next slide. Let I move to your next slide. Right. Now, stability factor. So now we understand that so IC should not vary in spite of your leakage current or in spite of your base to emitter voltage or in spite of your current gain. So now the rate of change of now stability factor is defined as the rate of change of your collector current with respect to the collector leakage current at a constant beta and IB base current is called as a stability factor. So now here it is denoted with the letter S. So now we have three types of stability factors as it is mentioned as S is equal to S and S dash as well as your S double dash. So now your stability can vary based on your leakage current, based on your beta, which is current again, as well as the base to emitter voltage. So hence now, so stability factors are we have three stability factors. One will be S, another one will be S dash, another one will be the third one will be your S double dash. So now, so stability factor S, so here it is the ratio of the change in collector current with respect to the change in leakage current. So whereas S dash, so we have to keep when I wanted to find the stability S due to the reverse saturation current or the leakage current, we have to maintain the beta as well as the VB must be constant. Next, so to find out your S dash, so it is defined as change in collector current with respect to the change in base to emitter voltage. Now, so in order to obtain this S dash, so we have to keep the reverse saturation current or the leakage current and as well as the beta factor must. So out of the three parameters, two must be kept constant and one must be so varied here. Now S dash if I wanted to find, then beta must be beta as well as here you have to maintain the IC naught are constant. Next, in order to find S double dash, so we have to keep the base to emitter voltage as well as your leakage current must be kept constant, and we will find it by taking the ratio of changing your collector current with respect to the change in your current gain of your circuit. So now in our voltage divider bus configuration. So this is your stability factor with respect to your reverse saturation current, which is equal to beta plus 1 into 1 plus RB divided by RE by beta plus 1 plus RB divided by RE. So now next next slide. So this is your how to find your stability factor in a fixed bias circuit. Now the stability factor ideal value is 1. Now here always the low possible stability factor is required one than the high possible stability factor, because we don't want to change the collector current in spite of the three parameters. So if it is the denominator is having more change, then our steady so our numerator, which is your change in collector current, if it is less, then the lesser values of your stability is suitable with a high stable. We'll treat that as a high stable circuit. So high stable circuit is with a low possible values. So poor stability circuit yields with a stability which is high values. So now always the ideal value of stability factor is equal to 1. Now in a fixed bias circuit, so where we connected your VCC. So this is a circuit. We have fixed bias circuit already we have discussed it, right? So now in a fixed bias circuit, like what we have is, so one transistor. One second. So in a fixed bias circuit, we have a transistor with a common source, which is coupled with a base resistor RB to the base of your transistor, as well as it is also coupled to the collector through a resistor RC. Now, so now let I am just drawing that circuit. So this is your transistor in a fixed bias circuit. Emitter is grounded. Next, collector is coupled. where common VCC. Here we have a plus VCC. Next, your base is coupled with a resistor RB. So amount of voltage is here it is VBE. Base to emitter junction voltage is your input voltage. Now amount of current through the resistor, if I treat this as a I1, then our current IC is equal to, so this is a common emitter configuration circuit, hence it is IC is equal to beta IB plus beta plus 1 times of IC naught. Now, if I wanted to find the stability factor S, so I have to have a change in IC with respect or dou IC divided by dou IC naught. Now, let I am just dividing this expression, the above expression on both sides with respect to your IC. Then we have on your LHS we have 1, on your RHS we have beta times of DIB divided by DIC plus of beta plus 1, as beta is a constant, so beta plus 1 into DIC not divided by DIC. So now this one is equal to beta times of DIB divided by DIC plus of, as we already know that S is equal to change in IC with respect to the change in IC naught. Now, so the since your change in IC and IC naught, the differentiation of the IC naught divided by differentiation of IC is equal to 1 by S. So hence here S is equal to beta plus 1 divided by 1 minus of beta into, so DIB divided by DIC. Now, the stability factor in your fixed bias depends on your beta, as well as it also depends on the base current. Next, it also depends on the collector current. So now, if we change the base current, then obviously it will be changed with the output current is also changing. Then the stability factor always now it is depend on your, so pure I mean so delta IB divided by delta IC, because IB current is fixed since we are transferring this current I1 to the base of your transistor, where I1 is equal to VCC divided by RB. So VCC divided by RB, where VCC is a fixed magnitude and RB is the fixed resistor value. So when I1 is fixed, then your DIB by DIC become zero. When it becomes zero, because it's a constant, so your base current is constant. So differentiation of your constant becomes zero. Then 1 minus of beta into 0 is equal to beta into 0 is 0. So 1 minus 0 is, we have in the denominator 1. So stability factor of fixed biasing is equal to beta plus 1. So substituting this in your previous equation, we will get S is equal to beta plus 1 times will have. So beta is around 400 plus 1. So but as we already discussed, so we require the lowest stability factor value, not the higher range values. So now the lowest is the best stabilized circuit, whereas the highest value of a stability factor is to the poor stabilized circuit. Hence here, but the thing in fixed bias is the circuit is very simple. Next, only one resistor RE is required for improving the biasing conditions or for improving your stability. Where here we connected your emitter to ground. Instead of that, we can connect the emitter resistor and we can control your IC collector current, which does not change based on the base current variation or your leakage current variations or the temperature variations. Right. Now, next. In the next slide, we have your stability factor in the voltage divider network. So now this is a voltage divider biasing circuit where we have divided, instead of connecting RB resistor directly, we have to go two resistors R1 and R2 and just taken the Thevenin equivalent also. So what is the amount of voltages in the voltage divider network, and what is the input currents and output currents, so IB and IC. are the IB is the input current, IC is the output current. Where here emitter one more resistor. Now instead of grounding your emitter, let me connected your emitter to your resistor RE. The amount of voltage which is dropped across your VE can manage your increment or decrement in the collector current. Now, the stability factor S in your voltage divider is beta plus 1 times into 1 plus R naught by RE divided R Thevenin. We have just the last slide. We just discussed this as a R Thevenin. Now, R Thevenin is equal to the parallel combination of R1 and R2. So, beta plus 1 times plus of R naught divided R Thevenin divided by RE. Now, stability factor here, if we have taken the ratio of R Thevenin divided by RE is very, if we are treating those, if we are taking those values, the ratio of here R Thevenin divided by RE is very, very small. Almost your beta factor, your stability factor S is equal to 1. Hence, so this yields to your ideal stability factor of a well stabilized biasing circuit, which will have ideal value of 1 that we can obtain from a voltage divider network or a voltage divider biasing circuit. So hence, so here, so out of all the biasing circuit, voltage divider biasing circuit is the most suitable biasing technique for more stability. Right, with that we'll have the faithful amplification at the output without any distortion. So next slide, we'll move to our bias compensations. Now, compensation techniques uses your temperature sensitive materials. So where the temperature sensitive materials are your diodes, transistors, thermistors, and sensistors, etc. Now, so this can maintain your operating point at a constant or at a fixed position. Now, let me move to the diode compensation. Thereafter, we'll move to the thermistor and sensistor compensation, which can maintain the operating point at a fixed position. Now, here diode compensation, which will have the instability due to your VB variation, as well as two circuits we have. So might the operating point will vary based on the VB based to input junction voltage variation, or it might vary due to your output leakage current variation. So two circuits we have to discuss. So now first one, they will now one second. Diode compensation technique due to your VB variation. Now already we know that you are taking your transistor which is of a semiconductor silicon, as well as the same type of silicon material we are taking to construct your a diode. So with the same cut-in voltages, with the same properties we are taking. Now let me take about VBE. VBE, if we change the VBE, how it changes here, IC collector current. And after connecting a diode in a particular at a particular terminal, how it compensates that increase in VBE can change your collector current, that we are going to discuss now. So now, so this is your voltage divider biasing circuit. Now in this voltage divider biasing circuit, we connected a diode. So at this emitter terminal, so like we connected your cathode to the emitter resistor, and anode is connected to the common. Then next one more resistor we have taken, which is RD, and we provided one more supply with the negative supply to the cathode through a resistor RD, and positive supply is connected VDD we have taken. Now this amount of applied voltage VDD can make your diode to on position, because we are properly forward biasing this. And here we connected your positive terminal to the anode, whereas negative is connected to RD to the cathode of the diode. Now here, just look at here, the diode D is forward biased by the source of VDD and through the resistor RD. The variation in the VBE with the temperature is same as the variation in the VD. So the effective amount of applied voltage at this base to emitter junction is equal to VBE minus of VD. So now, if base to emitter junction voltage increases, the same amount of voltage, because we are taking this transistor of silicon with the same type of material, so with the same parameters as like a diode. Hence, the effect of change in VBE also changes the amount of voltage drop across your diode. So like this, we can compensate. So if you have an increment here, then that same amount will be affected on this, so which is nullified here. And due to this, so the amount of collector current is maintained constant. Now, so here the current remains constant in spite of your variation of your base to emitter junction voltage. Next, we'll move to your next slide. So how to provide the diode compensation with the instability due to your reverse saturation current variation. Now, amount of current. Now, instead of connecting, so in your VBE variation, we connected with the emitter, whereas here we connected at the base of your transistor and replaced your R2. So now the amount of I is equal to here amount of current passing through the R1 is equal to I naught plus of IB. Now amount of input current is equal to I minus of I naught. Amount of current passing through the R1 is equal to IB plus of I naught, where IB is I naught or ID. This is the diode current. Let I take this as a ID diode current. So IB is equal to I minus the I naught. So now for a germanium transistor, I'm taking a germanium transistor. So germanium transistor, then it is equal to VB equal to 0.2 volts for base to junction 0.2 to 0.3 volts. So which is very small, and neglecting the changes, neglecting your changes. So IB plus of I naught, IB is equal to I minus I naught. So now total amount of current here, it is equal to VCC by R1, where VCC is a constant because it's a DC supply voltage. So it doesn't changes with respect to time. So hence your VCC by R1, which is constant. So now as we know that in your common emitter configuration, IC collector current is equal to beta times of your IB plus 1 plus beta times of IC naught. Now, so here let I replace that base current with the I minus of I naught. When I replace that I minus of I naught, here we have here, if our current gain almost it is 500, so beta is far greater than your 1, will get IC collector current is equal to beta times of minus of beta times of your diode current plus of beta times of your IC naught. So now the amount of current flow through your R1 is just here the voltage drop across here R1, which is nullified with the current which is passing through the diode, which is beta times of diode current IB. So hence here I naught is approximately equal to your IC naught. We get it as IC is equal to, sorry, diode current. Now if diode is under reverse bias, so hence here, so when the diode is under the previous slide, just look it out here. Diode is connected in a reverse bias mode. The amount of current flow is a reverse saturated current. So that amount of current now, if it is flowing through that diode plus of beta times of IC naught. This is due to your output junction reverse bias. So now if I'm taking your both transistor of same type, so now it is multiplied with the beta times of diode current plus of your beta times of your reverse saturation current of your collector to basing. So these two might be cancelled. These two are cancelled. Then our collector current depends on the fixed amount of current which is passing through the R1. So like this, so if as I is constant, IC is also remains constant. So we can say that so the changes in your reverse saturation current with the temperature are compensated by the diode collector current. And so with that, so your current output current maintained at a constant value. Hence, the quiescent values or the operating voltages, operating points may not shift from center of the DC load line. So next, next thermistor compensation. Now that I'm taking a temperature sensitive device, which is a resistor we are taking, and that resistor which is having a negative temperature coefficient. What does mean by negative temperature coefficient? If the temperature increases, that resistance will decrease. If the temperature decreases, the resistance will increase. So now how to compensate the amplifier with a thermistor? So how to compensate that amplifier with the thermistor? Now we connected the thermistor at the collector to the emitter terminal. Now here amount of current flow through the emitter resistor is equal to summation of your emitter current plus of your thermistor current flowing through the thermistor. Now here amount of voltage drop across your RE is equal to IE plus IT into of I. If temperature increases, then amount of resistance will decrease. When amount of resistance is decreasing, then IT increases. So thermistor current increases. If IT increases, the amount of voltage drop across here RE increases. When the voltage drop across here RE increases, then the amount of base to emitter junction voltage, the effective amount of base to emitter junction voltage which can put your transistor under active region will reduce because VBE is equal to VB minus of VE. VB minus of VE. Now, as temperature increases, next, in resistance of thermistor decreases. When thermistor resistance decreases, IT, the current through the thermistor increases. When that increases, then amount of drop across here, RE increases. When it is increasing, VE increases, which can reduce your base to emitter junction input voltage. So when base to emitter junction voltage decreases, then amount of IB reduces, which means here when IB reduces, then automatically your IC also reduces. Like this, we can compensate the increase in the collector current due to the temperature increase by connecting your thermistor at the collector terminal. Next technique is your sensor technique. Now, in the sensor technique, same circuit we have taken, but we have connected that sensor at your base terminal. Since your sensor is having a positive temperature coefficient, so temperature increases, then resistance increases. Temperature decreases, then resistance decreases. Now, so if temperature increases, so which is connected R1, which is parallel to the with RE. As temperature increases, resistance of the parallel combination also increases. Then thermistor and R1 increases, their voltage drop also increases. So this decreases the voltage drop across here R2. This decreases here. So here these two are in parallel combination, sensor and R1. So now amount of current flow through the R1. So the parallel combination, if it is increasing, the drop across this become more, then the drop across this R2 becomes very less. So when amount of current flow through this resistors R1 and R2 increases and the amount of voltage drop across your R2 decreases. When amount of voltage drop across your R2 decreases, then base to emitter junction voltage also tends to decrease. So here when it is when temperature decreases, then again it is moving into a cutoff region. So in order to stabilize that, what we have to do here, so this parallel combination of resistance decreases, then drop across this becomes less, whereas drop across this R2 becomes more, when drop across your R2 is more, then that you are applying to the base of your transistor as base to emitter voltage. So which increases the base current, which is your input current. By that, so collector current is increasing. Like this, we can stabilize your output or a collector current with a variation of your IC naught or VB and theta. So with this, we have concluded here the stability, thermal runaway, as well as we also mentioned the compensation techniques here. So with this, we have finished with this concept of biasing. So next class, we are moving to the CE amplifier analysis. Do you have any doubts? We started 10 minutes late, right? Here today. So it will be extended more 20 minutes. Don't mind that for today. In the next class, I'll give you a 20 minutes of break time. Okay, I'll wind up as early as possible. Okay. Is it clear, everybody? You can answer your test. The test already started. Please answer and log out.